Okay, say we did our first application of the Navier-Stokes equation to the case of parallel shear flows. And I'm not going to go through the whole solution here, but I want to more outline the general class of flows that this considers. So what we're focusing on are flows where the velocity vector consists of only one component. This is u0, 0. And that one component varies in only one dimension and is steady. So for example, velocity varying, velocity in the x direction only and varying in the z direction. What makes them parallel is that the flow is all in one direction, and the shear flow means that it varies only in a cross flow direction. So this could be z, it could be y, same application. The fact that flow is steady, and then we're going to further assume that the x and y derivatives of velocity are 0. And with that, our Navier-Stokes equations become simplified to the point where we would say that d squared u dz squared is equal to some constant value. Now that constant could be related to the gravitational constant, could be related to a pressure gradient, or could be 0 in the case where we have boundary-driven flow. Parallel shear flow in the x direction needs to be defined on a domain where we have, say, z axis going upwards, the x-axis horizontal, and we go from z equals 0 to z equals h. So we need a boundary condition at z equals 0 and a boundary condition at z equals h. So we have two boundary conditions, which are required because this is a second-order differential equation. Integrating that twice, we get that u of z is equal to, say, 1/2 a z squared plus, that should be 1/2 c z squared plus az plus b. So c is the constant that comes from our governing equation. A and b are integration constants. Those integration constants then need to be evaluated by the boundary conditions. Evaluated with boundary conditions at z equals 0 and h. And with that, you then have the complete solution. We did a few different examples in class of cases where the plates were moving on either side, or the boundaries are moving, or that there was a pressure gradient or not a pressure gradient, or flow down an inclined plane. Really, at its core, all of these solutions have the same mathematical form.